Professor, you're on mute.
Okay, can you hear me now?
Yeah.
Okay, great. Thanks. Sorry about that. Um, okay, where was I? Yeah. So as I mentioned last time, we're going to be working our way, in addition to the lectures, through Project 3. I will probably post the full assignment tomorrow or Friday. I will, I told you a little bit about it on Monday, and we'll do a little bit more related to it today. We'll talk about Anaconda and Jupiter again today, and I'll give you some examples. I'll kind of work through Lab 11 in Jupiter and show you some of the features there that we'll be using in the assignment to get you up to speed. Assignment 3, program 3 will be due again tentatively the 4th of December, so you got plenty of time. Presuming you're working well at it now. Going through tonight's lecture, though, I did want to cover things that are not powers of 10, things that are not decimal numbers, binary and hexadecimal numbers in Python. And boy, that's an embarrassing typo because it's spelled hexadecimal numbers. Sorry about that. Binary numbers are base 2 and hexadecimal numbers are base 16, and they're very useful in computer science. They appear a lot. And so Python has built-in support for them. So we do want to walk through all of that. The only administrative notes to talk about are there's more program 3 stuff in tonight's lecture, and make sure you get lab 11 done. The majors are taking their exam this week, so there's less stuff going on than normal. And let's get on today's lecture material. History lesson, ancient history lesson. We as humans count things by powers of 10 because that's how many digits we have. Most people, obviously there are exceptions, have 10 fingers, 10 toes. So you count to 10. And we have, over time, developed a total of 10 symbols. Used to only be 9 until the Mayans added in the 10th symbol called 0. So in human natural language, we know the 10 symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And there are 10 of them, as you see, since we always start counting at 0. Again, historically, that's because in the old days, people could count on their fingers or their toes. That's how many you have. It's natural. But that's not the best way for machines to count, because the earliest digital computers, and really almost all digital computers even today, are made up of a series of electrical switches. And electrical switches have 2 states, on and off. Current flows or it doesn't. In many cases, actually, what happens is voltage is held at plus 5 volts or voltage is held at minus 5 volts. If the electrical potential is plus 5 volts, that's a 1. And if the electrical potential is minus 5 volts, that's a 0. But conceptually, we kind of teach it as electrical switches, on and off. Anything that's on is a 1, and anything that's off has a 0. And I can signal anything I want to you using just these 1s and 0s. And something that only includes 1s and 0s is called binary number. We only need the 2 digits, 0 and 1, to represent all numbers. The 0 and the 1 in this case are called binary digits. Now, again, as I've been saying throughout the semester, computer scientists, and I am one, tend to be lazy. And so if we can shorten anything, we do. And so binary digit was a pain to say, so it got shortened to bit. So if you wonder where the term bit in computer science came from to represent a single value of 0 or 1, that is exactly where it is. Bit is short for binary digit, and it's a single value 0, 1. So that's where bit came from. Now, there's an old joke. There are 10 types of people in the world, those who understand binary and those who don't. Sorry, I'm a father. I have bad dad jokes. That's all I've got. I'm not a comedian. That's why I teach computer science. A binary number is something that's really easy for the computer to understand, but humans don't. So anytime a human wants to use a binary number, we have to figure out what it is in human speak, in decimal. Now, fortunately for us, in both binary and hexadecimal math, places are the same as in decimal. In other words, the least significant bit, the least significant binary digit is always on the right when it's written for humans, and the most significant is always on the left. If this were a decimal number, we'd put a comma here, and we would say that this number is 10,000,001. Okay? If this were decimal, that would be 10,000,001 reading from left to right. But this isn't decimal, it's binary. So everything shifts every time we shift one place to the left, we change by a power of 2. Now, the rightmost digit, the least significant bit, is always something times 2 to the 0th power, or 0 or 1. So this digit, the one that's highlighted right here, the 1 in this case, is always just a 0 or a 1. The next one over is 2 to the 1st power. Just like with digital, it's 10 to the 1st power. This is 2 to the 1st power, or 2. This is 4. This is 8, 16, 32, 64, and this is 2 to the 7th power, or 128. So this 8-bit string here, this thing of length 8 bits, historically is called a byte, spelled B-Y-T-E. That's a byte in computer speak. If you're into computer networking, it's called an octet because it's a group of 8. It's often called a byte, most often called a byte in computer science. A byte is just 8 bits taken together as a group. Okay? So the computer can understand this fine. How do we as humans understand this? Well, we look at this and we say, well, this is 1, and this is 1 times 2 to the 7th, or 128. So the value of this byte, the value of this octet, is just 128 plus 1, or 129. So this is how you represent the decimal 129 in binary. And so this is something that the computer does all the time. You say 129, it converts it to that. Okay. Now, units of 8 are quite common, as I said, in computers, not as much as they used to be. Everything is 32 or 64. It's all powers of 2, but it used to be you had to deal with groups of 8 all the time. So people pretty much knew every value. There are 256 different values. If every bit is a 1, and you can do the math on this, this equals 255. So the biggest value you can store in 8 bits is 255. Okay, so if you need more than 255, you need more bits. This is another example of the same thing. This is just 128 plus 64 is 192 plus 32 is 226, 230, 232. This is 232 in decimal. Okay, you just figure out what each one means. You can add these things together, and it mostly just works like decimal math with carrying. If you're going to add, you start on the right and you carry when needed. The difference is, since you can only go 0 or 1, there's a lot more carrying. So 1010 plus 110, we go 0 plus 0 is 0. We go 1 plus 1. Well, okay, 1 plus 1 is 2, but remember there is no 2, it's 10. So in binary, 1 plus 1 is 10, which is a 0, carry the 1. Carry a 1 in this column. We have the 1 carried plus 0 plus 1, that's 10. That's a 0, carry a 1. 1 plus 1 is 0, carry a 1 is 10. So 1010 plus 110 is 10,000 in binary. Subtraction, you start on the right and you borrow for the next place over when needed. You can quickly convince yourself that 1010 minus 101 is 101. 0 minus 1, we have to borrow the 1. 10 minus 1 is 1. That became a 0 when we borrowed. 0 minus 0 is 0. And then over here, 10 minus 1 is 1. So basically, binary math works the same as decimal math. Multiplication, you go column by column. Division can get ugly, but we're not going to worry too much about that. So in general, if I need to convert from decimal to binary, because I as a human think decimal, not binary. When I worked full-time as a network engineer, I pretty much thought in binary, but not since then. If I gave you the decimal number 10,000,001 and asked you to tell me what it is in binary, you have to subtract powers of 2 from it until you get 0. So what is 10,000,001? Well, remember that what I'm trying to show here, I'll work through and hopefully this can understand it. Okay. The first digit and first bit in any binary expression is the zeros. This is 2s. This is 4s. This is 8s. This is 16s. That's 32s. That's 64s. And that's 128s. And there should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Right. So now, as we've said, we have an 8-bit byte. We have a string of 8 bits. This can hold up to 255. Well, 255 is not going to give me anything near 10 million decimal. So let's keep going. Let's put a few spaces in there to separate. Okay. The last one we had was 128. Well, that's the number of 256s. That's the number of 512s. That's the number of 1024s. That's the number of 2048s. That's the number of 4096s. That's the number of 8,192s. That's the number of 16,384. That's the number of 32,768. And that's the number of 65,536s. So there should be 8 of these if I haven't messed something up. 1, 2, 3, 4, 5, 6, 7. Okay. All right. Yeah, that's right. I should have put a space there. There we go. So I gave you a table down below because I don't want to keep doing this forever because I am absolutely guaranteed to make a mathematical error. And it shows you that if I go out to 2 to the 20th, which is this, I'm at 1 million. 2 to the 21st is 2 million. 2 to the 22nd is 4 million. And 2 to the 23rd is 8 million. Now, if I want to convert, this is a long way to go for a bad thing, but if I want to convert decimal to binary, 10 million, I now have to figure out how many of these things do I need? Well, the answer is I need 1 of these because that's 8,388,000. So there's going to be a 1 right here. That's under the 0. Then I subtract that, and then I can work through and to, oops, sorry, I'm on the wrong slide. Work through, you could come up with the answer. And it's right here. So now I have this string of things that's 24 bits long. That is how you represent 10,000,001 decimal. Okay. That's how you work through it. Mathematically, that's fine. You are never going to have to do this by hand in this class, okay? There will be a little bit of binary math on the final, but trust me, it's only going to be things that you can do in your head without making any mistakes, because I'm not going to test you on how well you do binary conversions in your head, because I would fail such a test, and that's not fair. So this is how we do it. Fortunately, the computer does it for you. Python does this by indicating that a number is in binary by prefacing it with 0b. That's a numeric 0, not an O, and it's a little b. And that is binary. Okay, so let's go to PyCharm real quick. Give me a new Python console. Get rid of the code from last time because we don't need that. By the way, I finally, right before class, got around to putting the code from last time up on GitHub. It is there. Apologize for the delay. But now we can say something like count equals 0b 110111010. And that's fine. Now it thinks that count is a binary number, and I can say print count. And it will tell me, because print automatically converts to decimal, this will tell me that the decimal value of this binary string is 218. I'm not going to check it. I'm assuming that my Mac can do that math right. If my Mac can't do that math right, I have a problem. So if I calculated that, if I think that this is wrong, I'm in deep trouble. Anyway, this is just how Python handles things. If you tell it 0b, it says it's a binary number. Now, again, because it says 0b, you can only assign it ones and zeros. If I say count equals 0b 1, 2, 3, 4, it's going to tell me no, wrong. You said binary. Binary is only ones and zeros. This 2, 3, 4, and it's going to stop as soon as it hits the 2. It's not going to get to the 3 and the 4, is invalid in binary literal. So in this class, we don't do a whole lot of programming with binary or hexadecimal, either one. We mainly introduce you to the idea because that's how computers work behind the scenes. Why is that? Why computers work? Because everything is on, off. Everything is plus 5, minus 5. Everything is a switch. That's it. Okay. So Python does include a lot of support for binary numbers, and it will check you. It will make sure that you're really treating something as binary only. Okay. Now, let's get back to the slides. And that's what this says, 0b. Good question always comes up, is this case sensitive? Let's find out. And the answer is no, it is not case sensitive. Python doesn't care if you say 0 little b or 0 big B. Now, I will warn you that if you program in other languages, you will find places where it is case sensitive. You will find other languages where it would scream when you said 0 capital B to indicate a binary. So it is good practice to get in the habit of just using the smaller letters. Use lowercase letters when indicating binary or hex. So that's what we're going to get to next. But Python does not care. Python is not case sensitive. It's okay if you use an uppercase letter. But again, it's just better for all your programming needs in the future. Go with the lowercase letter. It's just habit to get into. Okay. And again, this is how Python works. Python does include a function called bin to convert. Okay. So I equals 543. Let's just say binary version of I equals bin of I. You know by now that this is a function. There's code somewhere in bin that converts this automatically for you, and that's going to return it and it's going to return something of value binary digit, which is fine. And now you can see that if I look at the value, I have a binary string. I have a binary digit. So if you need to convert to binary, just use Python. It's got a function automatically built in. But you should be able to do it. It's like anything, right? You know, balance your checkbook with a calculator. You know, check your arithmetic with the calculator. But you really should know how to do it in your head, just in case every single device you have fails at the same moment. You should really know how to do the math in your head or with a pencil and paper. That is binary. Now, some things get really, really, really big. Let's go back to that case where we had this number in bits. Okay, I couldn't possibly remember that number. That's just a long string of bits. Okay, there needs to be an easier way for humans to keep track of it because we're not machines and we don't work the same way despite what the AI people want. And so that's why people, not machines so much, but people deal with hexadecimal or base 16. Why hexadecimal? Why base 16? Because it's 4 bits together. It's easy to handle 4 bits together, and think about it. Yeah, 8 bits is a byte. It's 256 possibilities, but 256 possibilities is kind of a lot to remember. It's really, I mean, you really got to be someone who's devoted to dealing with network traffic all day long before you can look at any random combination of 8 bits and tell somebody what the decimal value is. But base 16, that's easy. Hexadecimal, that's easy. So why hex? It's just 2 to the 4th power. It's an easier thing to deal with than binary, but it's closer to what machines do than decimal is, so it seems like a good combination. So hexadecimal, or hex for short, is base 16, and when you deal with programming and you deal with networks and you deal with a lot of other things, you will see hex all the time. Now, the first problem we have is digits, is representing hexadecimal digits. Okay, let's go back to binary. All we need is 0, 1. Cool, we got a 0, we got a 1, we're set, not a problem. 10, right? Digits, we got a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's easy. We know that. We've done that all our lives, you know. My wife works in special education at the local public schools with kindergartners in 1st grade, and they know all the 0 through 9. They can deal with that. But 16, what do you do? So the convention is that since you need 6 more symbols to make 16, right? We get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 more, we use the first 6 letters of our alphabet, A, B, C, D, E, F. So the convention we use is that our digital 10, our base 10, 10, is referred to in hex as an A. Our 11 base 10 is a B, 12's a C, 13's a D, 14's an E, and 15's an F. So if you start seeing things that look like strings because they have A's and A's through F's in them, that's hex. Okay. Now again, Python is not case sensitive. Conventionally, we most often with hex use capital letters. We most often use uppercase letters to represent these A, B, C, D, E, F, 10, 11, 12, 13, 14, 15 in hex. But again, Python is not case sensitive. Either an upper or a lower case will work. And again, hexadecimal base 16, that seems to be a reasonable compromise. Most people with a little bit of practice can deal with a 0 through 9 and these 6 more A through F. Okay, you will find that you very easily can start looking at strings of hex digits and know exactly what it is. Okay, because you could deal with 6 extra symbols that you're familiar with. if you had to go, 8 bits and 256 different values, and we needed another 246 symbols, no way. It'd be like the names of hurricanes this year, right? Nobody would actually remember what there is. I mean, how many people actually remember that there was a hurricane called Isaias that they were worried was going to hit Maryland? It seems like 5 years ago. I'm old, but it seems like 5 years ago. It was this year. So remembering that many symbols would be like remembering hurricane names. Couldn't do it. But 16 seems to be decent. Now, when you're converting decimal to hex, it's similar to binary, right? And again, there's a built-in function in Python that does a conversion for us. It's just hex. And the one thing I left out of this slide is in Python and in every other language, 0x means a hexadecimal number. They don't use H, they use X. 0x is a hexadecimal number. Okay, so if I say num equals 0x 1, 2, 3, 4, Python now knows that num is a hexadecimal number. And the print function automatically converts to base 10 for us and says that's 4,660. How we as humans would do it is like this. Let's go back to the slides because I need a place to work on. And I'll bring up a new text box. 0x 1, 2, 3, 4. The most significant digit is to the left. We ignore the 0x. The 0x is just a marker. The 0x just says this is hex. It's not part of the not part of the number. This is 16 to the 0th power. It has this units value. This is 16 to the first power. This is 16 to the second power, which is 256. And this is 16 to the third power, which is, 4192 is what it should be. Third power. Oh, 4,000. You're right. 4,096. 2048 double, 4,096. Okay, that's 16 to the third power. So if I convert this to decimal, this is 4 times 16 to the 0, which is just 1, plus 3 times 16 to the first power, plus 2 times 16 squared, which is 256, plus 1 times 16 cubed, which is 4092, or equivalently, as we've seen this is 4 times 1, plus 3 times 16, plus 2 times 256, plus 1 times 4,092. And if we add those up, that's 4092, 768, 48, and 4. Okay. And that gives us hopefully the same answer that Python got when we did it here. Okay. This is 4092 plus 512. This is 512. This is 48. This is 4. And I'm going to take Python's word that it's 4660 because that seems right. So that's how you convert it manually in your head with a pencil and paper. That's how you convert decimal to hex and hex back. And again, fortunately, there's built-in functions that will do it for you. And in this class, you will have to do it with some really simple numbers to show that you can do it. You know the way to do it, but let's be real, we're not going to do any hideous conversions. Okay. And it would work the same way if you use those A's through D's. Okay, let's go back to PyCharm. Y equals 0x AB 543. J equals the hex value of the decimal number 391. So what's J? J is 0x187. Now we're going to add Y plus J. Interesting. Why did it do that? Y hex of Y plus J. There we go. That's an interesting little thing. I'm going to have to dig into why Python does that. It should have recognized this automatically as a hex number. It apparently didn't know. Apparently Python, when I typed this, did not, for some reason, partially treated that as a string, which it should not have, which is weird. I'll dig into that. The bottom line is it can do the math. It can convert the hex numbers together. This hex function just turned the digital number into base 16. Live demos. Oh, this lab 11 and Jupyter Notebook demo is going to go real well. Just giving you a spoiler alert here. I'm going to walk through how to do lab 11 with Jupyter Notebook. So that's I practiced twice, but we'll see how that works when I did live. Let's get back to Python hexadecimal and binary numbers. So converting decimal to hex, algorithm similar to binary. There's a built-in function that does it. 0x is what means a hexadecimal number. It is not case sensitive. Upper or lower cases are acceptable. Now, binary to hex is what's actually important. This is why hex finds its way into computer science at all, because again, the actual hardware underlying this everything is binary. Everything is on or off. Everything is +5 or -5. Everything is a pulse of light or no pulse of light. Everything is one of two values. But again, we as humans want to do this. It turns out that, of course, 16 is just 2 to the 4th. So what you do is you can group all 4 digits together. You can group 4 bits together, and that will represent exactly 1 hex digit. Okay? So what you do is a table that tells you, and I think that's the next slide, if you see 4 zeros, that's a hex 0. 4 ones, that's a hex 1. 0010 is a hex 2, and so on. 1010 is an A, 1011 is a B, C, D, E, and F. So you can construct easily a table that says for every group of 4 binary digits, for every group of 4 bits, here is the single hex value associated with that 4. And so if I give you a hideous long binary like this, and this you might see on a final because it is important to know, but it's really easy, right? If I ask you to convert this long string of bits into hex, it's real easy, okay? 1001 is 9. 1000 is 8. This is another 9. This is 6. This is 4. And this is 1. So here is this very long string of bits, 24 bits, and yet like that, off the top of my head, I can tell you that in hex, this is 0x989681. And now it's easy to refer to something. It's easier to explain something because the hex string is something I might actually understand. So this is why hex is important in computer science, because you can take these groups of 4 bits at a time and represent them with one symbol, one hex digit, and that makes your string now something that went from 24 to 6. And it becomes much more useful. Again, if I had to do this, if I tried to do this in groups of 8, it would have taken me 256 symbols. There's no way I could have come up with 256 symbols. That would not have made sense. So this is why hex exists. This is why it's important in computer science. And like I said, here's the general idea to convert. The numbers are prefaced with 0x to indicate they're not decimal. And I'm not going to go through any more. But that is what you need to know. Now, in this class, for the final, you'll have to be able to do some fairly simple conversions of binary to decimal, decimal to binary, binary to hex, hex to binary, decimal to hex. It's fairly easy. In this class, in Comp Sci 201, what we want you to understand this semester is that binary is how computers work. Humans work in decimal. Humans work in base 10 because most of us got 10 fingers and 10 toes. Computers work in base 2 because we got on and off. Okay. But only working in base 2, as you've seen earlier with the 24-bit long value, values get really big really quick. I mean, in computer security, the most common encryption algorithm you'll see, RSA, Ravesh, Shamir, and Adelman. You're talking about keys that are 2048 bits long. People tell you, you know, my key is RSA 2048. That means 2048 bits long for the key. That's an incredibly awkward thing to work with. If we compress it down to hex or something else, at least it's actually, you know, it's only 512 hex digits, which is still awkward, but it's more knowledgeable, more reasonable. Knowledgeable, it's a weird sentence. It's more reasonable to deal with. So what you need to know in Computer Science 201, and for the final, computers work in base 2, but that's long strings of bits. So we as humans often think about hexadecimal, which is just a group of 4 bits, base 16. Since we need more digits than we only have 10 in decimal, but we need 16 to represent hex. We use A, B, C, D, E, F to represent 10, 11, 12, 13, 14, 15. That's what you'll understand when you see A through F. That to represent a binary number in a Python program, you use 0B. To represent a hex number in a Python program, you use 0x. Python is not case sensitive. Some other languages are. And that'll get you started. And if you take 202, which is in C++, you will actually do a lot of hex programming. You won't do a lot of binary programming unless you take a computer hardware class. But if you take 202, which is C++, you will actually do a fair amount of hex programming, so it's important to know. Okay, what's the comment? Octal. Octal is base 8. Yes, octal is also... octal with base 8 is also something that is used, but for reasons of human comprehension, not nearly as much as hexadecimal or binary. And binary is just the way the computer works, but humans tend to be able to handle 16s, and so most people go into hex. Octal used to be common when people thought humans couldn't handle more than 8s, but it turned out that most people who care about this stuff can go to 16, so that's why it is. Okay, but yes, very good question. Excellent question. Base 8 is important. Okay. So that is the actual technical content of what I wanted to talk about and what you need to know about binary and hex. And it's cool stuff. You can play around with it all you want. But from what we need to talk about now, what I want to do is go back to some of the things we've talked about on Monday for Project 3 and work through it and get a little practice. Hopefully, you've all had a chance to install Anaconda Navigator Individual Edition, which is free. It's open source. Don't get one of the ones you have to pay for. If you do, okay, it's not wrong, but please don't waste your money. If your company's paying for it, waste their money. But Anaconda, and then from Anaconda, you can bring up Jupyter, and we're actually going to do the work in Jupyter. Anaconda also has the advantage that it has all these packages. If you've downloaded Anaconda Navigator and installed it on your computer. If you have the Windows version, it looks slightly different than this. It's not a huge difference, but it's a little bit different. This is what your home screen should look like. You've got Jupyter Lab, Jupyter Notebook. You've got a thing of PyCharm, but you've already got PyCharm, so ignore that. You've got another IDE that's equivalent to PyCharm called Spider, but it stinks. You've got some other stuff that we're not going to get into. What you care about on this homepage is Jupyter Notebook, because that's what Project 3 is about. What you also care about in Anaconda Navigator is this Environments tab where you see all the packages that you might have to go install. If I tell you you have to install a package, you can get it from, you should be able to get it from here. I don't think I'm going to give you any that aren't here. Okay. Now, last semester when I did this, I did not let them use Anaconda. I made them use pip. Pip is the package installer for Python. Some people prefer pip. It works, but it's awkward. So this semester, I will let you use Anaconda. At any rate, so now we have Anaconda running as an application on our computer. As I said, I have a Mac. The Windows version is just a little bit different. It's mostly going to work the same. When I launch Jupyter Notebook, what will happen is it will fire up a new terminal window on my Mac. It'll fire up a new shell, a PowerShell window or an app window on your computer, which will then launch a new tab on your default browser. So whatever default browser you're using on your computer, if this is working right, when you launch Jupyter Notebook from the Anaconda Navigator app, you should see something that looks like this. It's a new tab on your default browser. Now, my default browser happens to be Chrome. This is the latest version of Chrome, updated as of yesterday on my Mac. The default it goes to in Jupyter, when this tab opens, it shows me all the existing notebooks I have on this computer, so I can go back to the one I'm editing on or working on. Now, when you're starting out, okay, when you're starting out, you want a new tab. You want a new notebook. So I will go over here, right here, and I will select New. This means start up a new Jupyter Notebook for me. Okay? It gives me some options. It gives me Python 3 as an option, a text file, a folder, or a bare terminal. For our purposes, the only thing you need is Python 3. We're using Python 3 all semester. We want to write a Python 3 program. So I will say, give me a new Python 3. It's going to open a new, depending on how your browser sets up, it's going to open a new tab. If you have your browser set to open new pages and new windows, you'll get a new window. I've got Chrome set up that anytime I start something new, it's a new tab. So I have a new tab in Chrome, and it looks like this. This is a blank or empty Jupyter Notebook. Now, Jupyter Notebooks are a series of cells. I showed you on Monday, if you look at that, a couple of students' Project 3s from the spring and what they look like when they're finished with the graphics. I had them do some analysis of data on COVID infections in a number of countries as of end of April, early May. I'll give you a slightly different data set that'll be put out there. You will build a completed research report which integrates Python programming as your Project 3. And now the majors are going off and doing their own very separate Project 3. They'll do heavy-duty Python programming with very little how to present, how to integrate research, how to put it all together. That's because they're comp sci majors, and you're supposed to be learning, they're supposed to be learning the hardcore programming. You're supposed to be learning the hardcore programming and how to use it in your majors. That's why this course is different. So we will walk through this. I have my new Jupyter Notebook up. It defaults to named Untitled. As I said, I walked through this demo twice earlier today. And so that's why mine says untitled too. Okay, because I've done this a couple of times and I had some earlier things that started up as untitled. You can give it a name. When you give it a name, this gets back to this tab with all the Jupyter notebooks that you have on your computer, and Jupyter is capable of going through your Mac or Windows box and finding all the ones you have. So when I give it a name and save it, it'll be added here. For now, I'm starting it up. Okay. The key to Jupyter is everything is in cells. This right here is a cell. A cell is where I can put text. It's where I can put code, or I can put links to other things. Okay. Cells have you have to tell Jupyter what type a cell is. So by default, they're code. This little box right here tells you what this is. This is a new blank cell. It hasn't been assigned a type. So Jupyter thinks this is going to be for Python code. Remember, I told when I opened this, I said I want Python 3. So Jupyter thinks this is going to be Python 3 code. If I want to change its type, which we will do in a minute, I can change it to using that box. But for now, we're going to stay with code. Well, what kind of code do I want to put in here? I can put any Python 3 code. So just for kicks and grins, let's go get the Lab 11 code. Now, let's see if I'm still logged on. Let's see if let's see if I still got the terminal open. Here we go. If you go to Professor Hamilton's page on GL, directory in GL, and download the given scramble.py file, it looks like this. Okay. It starts up here. I used cat on GL just to print it out. And so here is the code in the given scramble.py on GL. So just for kicks and grins, I will copy that. Now I'll go back to Jupyter and I'll paste it. And now I have that program, that code you had, given scramble from Lab 11. I have it in a Jupyter notebook. And it's all here and it's all set. And I have the entire Python program. Now, obviously, it won't run because we haven't written our code yet. How do I know it won't run? Well, if you're going to run any Python code in Jupyter, there's a little box up here that says run, and you click it. And when I run it, you get the result down here that says invalid syntax. If you go up to the line that had the problem, alrighty. If you go up to the line that had the problem, that's because this is where you have to fill in the code. And in fact, if space question is not valid Python, that is what you would have to fill in, right? That's the assignment of Lab 11, is you have to fill that in. Okay. Now, I'm not going to give you the answer to Lab 11, but I'm going to sort of work you through it. What you have to do here, if you read the comments, is you have to figure out the base case for this recursion, for this filling out all the permutations of a string. Okay, I'm going to have a string, and I'm going to fill out all the permutations of it. What is the base case? Well, one base case is when I have all the string except the last letter filled out. Okay. Well, What does it mean to have everything but the last letter filled out? Let's look at our comments. Input. This is the scrambled work so far. Letters left is the letters left to scramble. Okay, so if there's only one letter or no letters left to scramble, then that's a base case, right? So let's go in here and replace this question mark, question mark, question mark, and say length of letters left. You can tell this is old code because we're using camel case, not snake case, is less than or equal to 1. That's a base case. Okay. Now, what do we do when we have a base case in this assignment? In Lab 11, for your recursion, what do we do when we have a base case? We just print it out. We just print out the string. Well, what is the string? If there's no letters left, then I just print out current scramble. If there's one letter left, I have to combine these. So I could write the code this way and say, now I will print out current scramble plus letters left, and that will completely solve my base case. Now, that is one way of doing this. You could also do it the following way. You could also say, if this is equal to 0, i.e. there are no letters left, then all I have to do is print out the current scramble. Either one of those will work as a base case for your problem. And then we can get this thing through and we can run it in Python. Okay, this base case will now work. So let's go back to set it the other way. And now I have to, in Lab 11, go down into the recursive case and figure out what that's supposed to do. Now, a lot of the code for the recursive case is given to you, right? Else, what I have to do is I have to start with each letter in the letters left, and I'm going to do all the permutations. I'm going to create something that's with each one of these letters. I'm going to remove the first instance of the letter. Remember, it doesn't recognize if there's two C's like CMSC. The two C's are treated differently. Talked about that on Monday. This just removes the letter that you're taking out from the string. And now you have to figure out what the new scrambled word was. Well, the new scrambled word is fairly easy, right? It's just what used to be the scrambled word plus whatever letter you're dealing with that you took out. Okay? And then when you do that, you can recursively call the function. Now, here's the thing. If you look at it, you notice that this function does not return anything. There are no return statements in this function. It returns none, as we know from studying Python so far. It returns none. There are no return statements. The reason that is significant is that what you can do, you don't need to call the function recursively, in an assignment statement. You can just call the function. You can just say, call the function permute and okay. And now all I got to do, this is old style programming. Don't worry about how it's main. We should have updated this to say if name equals main, whatever. But we have to have a call in the main program. You also have to have a call. And now I should be able to run this program. 1, 2, 3. And it gives me the 6 different ways to scramble the particular string. Let's run it again. Okay. Let's go back in here and run this one. And it gives me all the ways to do it. So this is how I use Jupyter Notebooks to do code. Now, why do we use Jupyter Notebooks rather than just simple Python code? I could use simple Python code and do this. What's the big deal about learning this other new tool? And the answer is you have the other cells to help you do other things, to help you explain, to help you share the results, to help you make the point in your research of what this is. Now, this just so happens to have been the first cell. Let's go back down. Let's move this cell down. We're in this cell. And let's see. What do I want to do? I want to move that cell down. Oh, always something. Yep. When I click the down button, that moved this cell down and created a new cell above it. Why? Because I want a header cell. Okay, now, so let's look at this new blank cell that was inserted above this. Here's my original code cell. Here's my header cell. Code. I don't want this cell to be code. I want it to be either a heading or markdown. We're going to start with markdown. Now, markdown is somebody's bad joke. Markdown is a takeoff on markup. Markdown is code, or is text that you assign symbols to give it meaning. This is how you get headers or anything else. What I'm going to do is I'm going to take this header comment. Now, again, this is not what you have to do for Lab 11. Do Lab 11 on GL like you've always done it. But this is how you would use Jupyter Notebooks. I've taken that comment out of the old cell and I've put it into the other cell. Now, notice that this is very different. Okay, this is very different because when I had it in this cell, it was just a Python comment. It was code. It happened to be a comment, but it was treated by Jupyter as code. Okay, and so that was why it was in the green and the little italics and everything else, because that's how Jupyter represents code by default. In here, it's something else. Specifically with Markdown, a single hash mark, a single pound sign, says, I want this to be a header 1. If you are familiar with Microsoft Word or Google Docs or anything similar, you know that you can go in and make something be a header 1, and a header 1 has specific properties. It's specific font, it's a specific size, it's specific bolding, italics, tabs, indents, space before, space below, all that's defined for a header 1, and you can change it any way you want to. Well, Markdown provides you the same capability, and by default in Jupyter's Markdown language, anything with a single in a text or Markdown cell, anything with a single pound sign is a header 1. If I deleted this pound sign, it's pound sign space, by the way, this becomes standard text. And so the difference between how this is represented and how that is represented is because this is standard text and this is still a header 1. So what you're going to do in Project 3 is you're going to also learn a little bit of Markdown so you can figure out how to present your results, okay, and how to do your research presentations and how to do your term papers and how to do whatever with Python code embedded, but with all the proper presentation. When we just did code, when we just did Python programs in CompSci 201, we learned how to turn in Python listings where graders read comments, which is cool because the CompSci 201 faculty and TAs read code. That's what we do. So reading comments is cool, but more generally, you probably don't want to go too deeply in that. You probably want to use your computer science knowledge to do the coding and your other knowledge to do the proper presentation in your major for whatever research you're presenting. Okay, and so you can play around with Markdown to see what you can do to make this different. Now, as I noted over here, if you look at this box which says Markdown, you can make it code. If you say it's all code, it's code. Markdown, we've already seen that. This is what happens if it's a run NB or raw NB convert. Don't worry about that. We're not going to be dealing with that at all. Or headings. Okay. And if you use headings, Jupyter tells you, and this is a good way to find out what a level 1 heading is, a level 2 heading is, or whatever. So for example, we've said a single pound sign is a level 1 heading, and this is the color and font and size you get. 2 headings is a level 2 heading, and that's a little smaller. 3 pound signs is a level 3 heading, and you can play around with it to see what you get. This is a Markdown cell. This is a code cell. And you can put them in between. You could put the function in a code cell. We could insert another cell. I'm going to take my main program and cut it out of that code cell. And this is a code cell down here. I'm going to put it down here. So now I have my functions all in one cell. And now I have my main program down in another code cell. So the point of this is Jupyter Notebooks is just a tool that allows you to combine professional presentation of your research results, the explanation. You are not limited to comment blocks in your code listing, combined with Python code that will actually run whenever you click run. Okay. So in this case, I didn't tell it to run the whole program, so it didn't run everything when I clicked it. But if I go up here to this and say cell, I want to run everything all. Now, even though this function and this main program are in separate cells and they're different things, and they may be pages apart on my listing, now they run exactly where they're supposed to. And now I will put in the string A, B, C, D, E, and it will run perfectly, and it will give me all of the 120 different permutations of a 5-character string. Okay. And so once you've got it working, it works. So that was the purpose of this part of today's lecture. In the first part of today's lecture, we did cover the computer science stuff that we're supposed to, specifically dealing with binary and hexadecimal numbers. You do have to know what they are and why they're important. That's going to be on the final. And you're going to use them in any future computer science you take. You do have to know, at least theoretically, how to convert. It really helps if you know also that Python provides some functions to do the conversions for you to make it easier. And that's what you need to know about binary and hex. And as somebody pointed out, Luke pointed out, there is octal as well. And there are other interesting and weird bases that sometimes can get used. From a mathematics standpoint, from my math background, I can pick base 13 if I want and do that. But from a computer standpoint, the two you're going to find really that you're going to run into are 2 and 16, bin and hex. Okay. Next week, we're going to get more into the other hardcore computer sciencey techniques, computer sciencey topics that we're going to cover in this class. Monday is the sorting and searching algorithms. And then Wednesday is the analysis and how well they work and when you should choose which one and, what assumptions are made and so forth. So we will cover those, and they're important to know. Pay attention to them, and they will be on the final in big ways. And we will also have more on Project 3. But like I said, since the last semester, we had some issues because by this time last semester in the spring, we were all virtual. I was doing this all remotely. And so we had most of the people who had issues with Project 3 had issues getting Jupyter up and running and installing all of the libraries, Pandas and Plotline and NumPy and everything that they needed. So I want to walk you through this now ahead of time so that we don't have those problems. And once we get into this, the problems that you'll have will be the actual Python programming, and we'll work from there. And as I said, really after exam 2, we've diverged greatly from the major sections. But that's because this is why this section exists, because they're going to go hardcore into here's how to program so I can learn how to program more stuff in C++ and Java and JavaScript and this and that later on. You're learning, yes, you're absolutely learning the computer science techniques. Yes, you're absolutely learning base 2 and base 16. Yes, you're absolutely learning quick sort versus insertion sort. Yes, those are important topics which will stay with you. You need to know, but you're also learning here is how this topic is relevant to me in my field, in my major, which may be different from computer science. So that's what's happening now. So get your lab finished. Do not use my code exactly. I've given you an outline for how to do it, but you better write your own code, right? You know how to do it. Just write your own code. It's due by Friday night. Please be working on the project. I'll put out a mention on Blackboard when I have the full project out on the GitHub. You already know Anaconda Navigator. Make sure you can download it, install it, and it works. Get the individual edition so you don't have to pay. Jupyter Notebooks. You want version 6.0.3. You want it running Python 3.8 because that's the version of Python we'll be running a class all semester. Make sure that works on your system and it's good to go. If you're having problems with Anaconda or Jupyter, talk to me. We'll get you some help because I don't want to come up that first week in December, which is the last week of class, and you're going, I've never figured out how to get Anaconda going. How do I get the project done? Well, you don't. Okay, so let's get this done now. Other than that, have a good weekend, and I will talk to you on Monday. And, of course, I'll be available if anybody has any lab questions or whatever between now and then. So thank you much.